Hello, and welcome to today's presentation titled Optimize Refinery Liquid-Liquid Separations. My name is Robert James with Paul Corporation, and it's a pleasure to be with you today. I've been with Paul for 33 years now. My current role is Vice President Marketing in the Energy Group with a focus on the oil and gas and refinery sectors. Some in the audience today may truly be fighting fires over water contamination issues. We hope that for you in particular, you'll find access to information on more reliable liquid-liquid separation equipment, allowing you to make more informed decisions going forward on how you may optimize and upgrade your processes. In today's webcast, we'll be covering liquid-liquid coalescer fundamentals, liquid-liquid coalescer products introduction, touching on a range of main refinery applications, final product, hydrotreating, mercury removal, sour water stripping, delayed coking, refinery intermediates, caustic treating, alkylation, acid gas removal. We'll close out with next steps to upgrading your processes and then open for questions and answers. So let's start off with a look at liquid-liquid coalescing fundamentals. Here we can see a picture of a coalescing medium with our flow from the left to the right side of the screen. Particles are shown as yellow squares. Droplets of discontinuous phase are shown as blue droplets, which we can see entering on the left-hand side as a very, very fine emulsion, progressively increasing in size until on the far side they have grown to much larger droplet size. We can see the importance as well of dealing with solids in any coalescing stream, and we can see in the matrix of the filtration we have a pre-filter layer, a primary coalescence layer, and then a secondary coalescence layer. So what does a liquid-liquid coalescer do? There's four main functions at work in the coalescing process. First is the initial capture of small droplets. These could be as fine as 0.1 micron in size, and this is often the measure of the true efficiency of a good coalescer, is its ability to capture these very, very fine droplets. Next, we need to have growth or coalescence of these small droplets into larger drops, up in the millimeter diameter range being pretty typical. Then we need the droplets to actually release from the coalescing filter medium, and final separation of these drops from the continuous phase by gravity or some barrier method. So if you have a lighter droplet, of course it will float if it's an oil in water, and if you have a heavier droplet, water in oil, it will typically settle. On this slide, we can see the force balance at work driving effective liquid-liquid separation. In a typical housing, let's assume we're working with a water droplet, we have an upward drag of the continuous phase trying to get out of the housing. This is FD, and we can see that it is proportional to the square of the radius of the droplet. This is being battled by the gravitational force, Fg, which is proportional to the cube of the radius of the droplet. So the important factor in coalescing is to make sure that we achieve a maximum stable droplet size so that the cube function outweighs the square function and we get effective settling, giving us good separation efficiency. So let's start to explore different types of emulsions. We've known for years that pure oil and pure water don't mix. However, emulsions come very, very close to full mixing. We can see examples here of the impact of surfactants in a water in oil emulsion or an oil in water emulsion. Surfactants are surface active chemicals that can be natural or that can be added to a flow. Natural surfactants include sulfur compounds from the production field. You can have corrosion inhibitors that are added, detergents that are added. Your actual additive packages that are in final fuels are very, very powerful surfactants. You can have a range of miscellaneous chemicals that are added for various reasons that contribute to the surfactant phenomenon. So here we can see reverse micelles in a water and oil emulsion. Oil in water emulsion has micelles that are present. Here we can see the impact of the surfactants on a reverse micelle of water and oil, where the polar ends of the surfactant have attached to the droplet, leaving the nonpolar end of the surfactant exposed. And this creates significant phenomena that make coalescing more challenging. One of these phenomena, steric charge repulsion, is when we see the exposed nonpolar ends pushing droplets apart. And this is one of the phenomena that helps create very, very stable emulsions, so that over extended periods of time, droplets will not even settle out due to gravitational forces. Another phenomenon that is seen is charge repulsion from different acids, bases, and ionic species that are inside the micelles. These tend to repel one another and are another active force keeping droplets from coming together or coalescing, creating a more challenging environment for any coalescer in a real-world application. It's interesting to examine surfactants and the impact they have on a phenomenon known as disarming, something seen on glass fiber media, one of the legacy approaches to liquid-liquid coalescing. What we have happening is similar to the reverse micelles. The polar ends of the surfactants attach to the glass fiber active adsorptive sites, which is where the initial droplet capture should be happening. And what happens in the disarming process is these sites are taken over by the polar ends of the surfactants and gradually render a glass fiber medium unable to capture droplets. This can occur after days, weeks, or months in service, depending on the volume and activity of the surfactants. But basically, you progressively deactivate or disarm the medium so that it can no longer effectively remove free water from the flow stream. So looking at some key points from emulsion separation, separation of oil-water emulsions can be defined by the interfacial tension measured in units of dynes per centimeter. And typically, as you increase the volume of surfactants present, you will see a lower dynes per centimeter number being measured. Lower IFTs are due to these surfactants. These are creating more difficult to separate droplets, as we saw, due to the surfactants, and are also contributing to the disarming effect. It's been noted that interfacial tensions, or IFTs, below 20 dynes per centimeter have been shown to be very, very challenging for glass fiber media due to these repulsive effects, creating for difficult separation. And then the surfactants gradually cause the neutralization due to the disarming effect. And once you have a fully disarmed coalescer, there is effectively no more water removal. What has been discovered is use of polymeric media provides high efficiency liquid-liquid separation. These media will perform without disarming. They are basically inert to the impact of the surfactant chemicals. They are able to work with the surfactants and orient so that if a surfactant attaches, it leaves the active polar end exposed to the main flow, and this provides the same capture function that is essential in continued coalescing efficiency. So these elements, when protected with adequate prefiltration to keep them clear of solids buildup, can last a year or more in continuous service. If we want to examine liquid-liquid coalescer performance measurement, first looking at water from hydrocarbon, one of the approaches is to measure the free water downstream in parts per million by volume per the Aquaglow method. This uses a fluorescein-treated pad that is calibrated to the free water content measure, giving us a value between 1 and 60 ppm of free water in the downstream flow. The Aquaglow kit is available from Gammon Technical Products, and we find it a very good piece of equipment to measure directly the free water content. An approach that's also commonly used in many labs is to measure total water ppm via the Carl-Fisher test. One of the challenges with the Carl-Fisher test is it does not tell you the free water content, and this can be very difficult to calculate due to widely variable water solubility in the hydrocarbon, which changes often due to the presence of the surfactants and the general makeup of the hydrocarbon stream itself. If we're looking at a hydrocarbon from water application, this is typically measured as parts per million total oil and grease. In looking at a liquid-liquid coalescer installation and performance optimization, it's important to note that a liquid-liquid coalescer removes free water, not dissolved water. You can get down as low as 15 parts per million or less free water, but after the coalescer, you can still get condensation of free water should you have a temperature drop and further condensation as very, very fine aerosols. So you always want to install your coalescer at the lowest temperature point. For example, at the end of a pipe run, usually atmospheric conditions will have the coolest conditions at the end of the run. So this will ensure maximum free water removal. Okay, so let's examine some actual liquid-liquid coalescing products. A typical installation of an effective liquid-liquid coalescer system includes a pre-filter followed by a liquid-liquid coalescer. The pre-filter is there to provide particulate control for long coalescer life. These can be either a horizontal or vertical orientation. Examples from Paul Corporation include Ultipleat High Flow, Marksman, Profile, or coreless filter styles, providing effective particulate control from the long life coalescer. The coalescing assembly is taking care of free water removal down to as low as 15 parts per million by volume, and these can be in either a horizontal or a vertical orientation to suit budget, size, weight, and footprint requirements. You can see an example of a vertical pre-filter and a horizontal liquid-liquid coalescer. Particulate removal in the pre-filter and the horizontal orientation of the liquid-liquid coalescer takes the flow from an inside-out flow direction in the coalescers, forming the droplets passing through the medium until they are large enough, in this case, to settle out due to gravity, traveling the far end of the housing until they settle out in the boot or the sump at the bottom of the housing at the far end. Here we can see a vertical liquid-liquid coalescing system. First off, we have a pre-filter once again flowing into a vertical orientation where the flow first passes into the top plenum in the housing. The flow passes down into the elements, passing from the inside to the outside, forming the larger droplets. Then these pass down and into the bottom separator section of the housing where, for example, the hydrocarbon flow will pass from the outside to the inside of the separator so that you have clean, water-free fuel or hydrocarbon passing downstream. The separator will resist the penetration of water droplets, holding them back so that they can collect on the lower tube sheet found in the housing and get removed as the aqueous phase, the discontinuous phase, now removed from the main flow, giving us effective liquid-liquid separation. One of the mainstream products that we offer is what we name our PhaseSep liquid-liquid coalescer. This is a fluorocarbon media coalescer available with either stainless or fluorocarbon end caps. Temperatures are good up to 149 Celsius, 300 Fahrenheit. Most importantly, this gives wide range of pH and chemical compatibility for these element styles. So these are very useful when we get into applications such as caustic removal or when we're running into higher temperature applications. The PhaseSep liquid coalescer is the product of choice. If we're at more neutral, lower temperature applications, the AquaSep family of LL coalescers is what is typically recommended. We have the AquaSep Plus coalescer that is designed to break the very, very finest in emulsions. The AquaSep XS coalescer, very effective fine emulsion breaking, and this is the workhorse for most LL separation requirements. The AquaSep EL coalescer, a coarser medium with coarser prefiltration needs. This is giving good economics on dirty streams while still offering excellent emulsion breaking capability. Looking at some of the product specs, we have good compatibility on hydrocarbons, ethylene glycol, methanol, isopropyl alcohol. We have a maximum operating temperature of 60 Celsius or 140 Fahrenheit and a pH range between 4 and 8.5. On the right-hand side, we can see a picture of the AquaSep XS coalescer on the top and the separator on the bottom portion of the element. Wanted to say a few words about the AquaSep XS and EL coalescers. These are new products in the Paul arsenal as of this year and offer tremendous range extension in our capabilities. What we're looking at is a product that will offer significantly lower CapEx footprint and weight, lower maintenance costs, less off-spec product, enhanced levels of productivity, better quality through features such as a 60% higher flow per element versus other styles within the Paul arsenal and within the marketplace. Water contents as low as 15 parts per million by volume. With the polymeric materials construction, you will see resistance to any disarming effect. We can apply these products in some of the existing installations and offer the potential to increase flow through the housing, reduce total cost of ownership, and achieve lower free water content downstream. So if you are presently using a PhaseSep coalescer in a neutral pH, low temperature environment, you may want to consider the AquaSep XS coalescer. Here we see the Aquacep EL coalescer. This is the new product that has a much coarser coalescing medium than anything in the Paul arsenal or many of the commodity products in the marketplace. This enhances the product's viability on higher solids loading applications. So let's examine the impact of these high-efficiency coalescers on some of the refinery applications that we've touched on. So here we'll be going through identified opportunities for enhanced water removal in key refinery applications. Let's kick off at the back end of the process, the important area, final product. Here we can see on the left-hand side various tankage, and we're passing through a particulate filter, we're passing through a liquid-liquid coalescer, and we may be either passing through salt beds with particulate filter downstream. There could be clay beds in the line if it's on a jet fuel stream, or possibly, as we see on the bottom line, the liquid-liquid coalescer is the last touch point before the flow goes out into the system. So the coalescer that we're recommending on final product is the Aquacep XS liquid-liquid coalescer. The customer benefits we can see on the right-hand side will include freedom from off-spec shipments due to high water levels, often seen with disarming conventional glass fiber coalescers. If you have a salt bed in the stream, you will see reduced salt costs due to the more effective removal of water. You're going to see elimination of interruptions and changeout costs due to replacement of disarmed coalescers, all for a very low cost per gallon being treated. Here we can have a few installations, a vertical coalescer on the left-hand side, horizontal on the top right, and a very small filter in the bottom center. This is actually a small analyzer filter, making sure that the analyzer achieved efficient protection from particulate and water contamination. Another important area is hydrotreating. Here we can see on the front end of the process application of a coalescer and particulate filter protecting the heat exchanger and the reactor beds in the hydrotreater, ensuring that they achieve maximum reaction efficiency, maximum bed life before the need for eventual changeout, and maximum throughputs. We can see on the downstream side, the right-hand circle, on the steam-stripped diesel stream, the importance of effective liquid-liquid separation. This is a very challenging application because of the very, very fine water droplets that are formed due to the condensation happening downstream of the stripping operation. And the liquid-liquid coalescers in the Aquacep family have been proven very, very effective here. Recommendations are to look at the Aquacep XS liquid-liquid coalescer on the upstream side to offer good protection of the catalyst bed, and Aquacep XS or even Aquacep Plus on the downstream application to ensure effective removal of the water and get as fine as clear and bright effluent downstream, good product quality diesel downstream of the coalescer. Here we can see some examples on a hydrotreating series of applications. On the top right, we can see the actual performance improvement in the quality. We have a hazy kerosene stream showing on the left-hand side of the picture, and a nice clear and bright stream on the right-hand side following coalescence. On the left-hand side, we can see a steam-stripped gas oil coalescer, horizontal orientation, and on the bottom we can see a hexane dehazing coalescer. Some refineries have the need for a mercury removal unit. Here we can see an example coming off of the crude unit. You have a lot of the lighter ends up top flowing into the mercury removal unit. We can see positioned upstream of that is a particulate filter and coalescer to ensure that particulate and water loading on the absorbents is reduced to a minimum. So application of the correct coalescer will ensure best mercury removal efficiency, longest beds before the need for changeout. So we can see the recommendation for the Aquacep XS coalescer on these applications. Sour water stripping is a very important process to handle a waste stream in the refinery. We've got sour water coming from many of the unit operations, atmospheric distillation, coking units, acid gas treatment units, and others, all producing sour water, typically collected in a centralized location. Here we can see a sour water storage tank that's feeding a heat exchanger and stripper column. Oil fouling and particulate fouling of the exchanger and column is a common issue, leading to many production limitation issues in the refinery. If you can't properly treat your sour water, you may have to bring down refinery production rates to a level where you can. If you have issues with oil carryover in your acid gas leaving the stripper column, that can affect sulfur plant operation, which again may press the need to reduce refinery production rates. And lastly, if your treated sour water going to the water treatment plant has too much oil, this is an overload condition on the water treatment plant. This can drive the need for reduction in capacity on the plant as well. So it's important to make sure that you keep this unit running reliably, and installation of a liquid particle filter and liquid-liquid coalescer will effectively handle solid and liquid contamination on the downstream equipment. What we're looking at is application of the Aquacep EL liquid-liquid coalescer, and when this is in place, there will be minimal fouling of the heat exchanger, of the reboiler, and of the column, so that the sour water stripper, the close plant, and the water treatment plant will not be negatively impacted by oil content and particulate coming from the sour water stripper system. Here we're touching on applications in delayed coker units. Coking is a process found in many refineries to take resid from the atmospheric or vacuum units and break these products up into value-added components. Typically, you will have your flow coming into the fractionator column, mixing with some of the material, doing a recycle in the loop. You typically pass up, go through the coker furnace, and part of the terminology here, the delayed coking, is due to the large volume of steam that's injected just downstream of the coker furnace to delay the onset of the coking reaction until you get into the coker vessels. So that large volume of steam injection eventually ends up as free water in the various streams coming off of the fractionator. So what we're looking at here is a requirement for high quality products that could be going to final product blending, that could be going to other unit operations, hydrotreating being a pretty typical one on many of the streams coming off of a delayed coker. And we're seeing the installation of particulate filtration and liquid-liquid separation to ensure high quality on these streams. So the Aquacep EL liquid-liquid coalescer would be the product of choice here, well suited to the relatively dirty environment on many of these streams because of the presence of the coke fines. but what you will be seeing is ensured product quality downstream, whether you're going into blending or whether you're feeding other unit operations. Here we can see on the bottom of the sketch an example of a unit on a coker gas oil stream, a horizontal liquid-liquid coalescer. Refinery intermediates, this covers a wide range of streams, typically where the flow is going from one unit operation to another. There is a need for continuous, efficient liquid-liquid separation. And what's often seen here is different types of legacy equipment. This can include mesh pack coalescers, electrostatic precipitators, sand bed coalescers, and API separators. What's been found is the separation efficiency tends to vary widely depending on the flow conditions, the interfacial tensions of the flow, and these can widely affect productivity, efficiency, create many gaps in reliability from where the refinery would like to be versus where they may be today. Typically, glass fiber coalescers have not seen much service on these types of applications, and that they are not suited to the continuous requirement with the disarming effect that we introduced earlier in today's discussion. So it's mainly the sand beds, the mesh pack coalescers, the electrostatic precipitators that are doing a lot of the work, have been running for many years, but are now being looked upon as an area for potential improvement. So what's recommended on these applications is to consider the Aquacept EL coalescer. This will handle the continuous nature very, very effectively, giving us water contents downstream as low as 15 ppm. You will not see any disarming in service. The life on these coalescers will be a minimum of 1 year when protected with the recommended Paul pre-filter, and pre-filter costs should be well controlled because of the coarse filtration requirements on the EL coalescer. Caustic treating is used extensively in the refinery environment. On the flow diagram here, we can see an example of a simple Merox treater. One of the issues with many caustic treating processes is that there may be trace carryover of caustic from these different caustic treating processes, creating high sodium levels in the fuel or hydrocarbon passing downstream. And application of a particulate filter and a liquid-liquid coalescer has been shown to be very, very effective in achieving high improvement of these flow streams. The FACEP coalescer, because of its compatibility in a high pH environment, is the typical product of choice here. Basically, in applications, you will see assured production, you'll see assured quality, making sure that you meet specifications for haze and sodium levels downstream. You'll be preventing downstream unit downtime if there's any further processing that may have been previously caused by contamination of catalysts or other issues due to the high caustic levels found downstream. Here we can see an example of a couple of installations. On the left-hand side, here's a FACEP coalescer on caustic removal from kerosene. On the bottom right, here's a FACEP on treating on light ends. Here we can see an example of an alkylation schematic where we have our flow coming in on the bottom left, passing through filters 1 and 2, pre-filter and coalescer, going into the reactor. On a sulfuric acid type reactor as represented here, it's so important to ensure free water removal to reduce reduction in strength on the acid. For every pound of water that gets in, there can be the need to replace on the order of 10 pounds of sulfuric acid. So that becomes very, very cost prohibitive. It's better to get the water out before the reaction process. Coming out, we see the acid settler, the caustic treatment, the flow then passing up, and to the top right we can see housings 3 and 4, removing any trace caustic carryover before getting into the deisobutanizer. Flow passes up and out the top and then down to the bottom right. We can see housings 5 and 6. There's a recommended placement here of a coalescer to handle large volumes of recycled water. With the recycle isobutane stream, you can have in the range of 1 to 3% water levels on this stream commonly seen. So this is doing a bulk removal before this stream mixes in with the olefin feed back into the unit. Up on the top left, we can see the propane stream coming off. There's often the need for trace caustic removal with filters 7 and 8 performing this function. So here we can summarize the product recommendations. If we look on the left-hand side, we can see application 2. This is suggested as the Aquasep XS coalescer. This is going to offer low process OPEX by minimizing the acid replacement requirements. You will also see benefit in high alkylate output due to the maintained strength of the acid solution inside the reactor. If we look at application 4, this is recommended as a FaceSep coalescer application, making sure that we get high quality alkylate meeting the sodium or caustic specifications for downstream product blending. If we look at application 6 on the recycle isobutane, the Aquasep XS coalescer is the recommendation here. This is handling the bulk flow coming from the deisobutanizer. 1 to 3% water, getting that out of the system is a good way to ensure minimal chance of upset inside the reactor. And application 8 on the propane FaceSep coalescers, stripping out any trace remaining caustic. And our last application to touch on today is acid gas removal. Here we can see a schematic of a typical system treating sour gas or sour LPG in the refinery via an amine treating solution. This produces sweetened product. One of the main issues is contamination of the amine from particulate and oils, causing foaming issues, causing fouling in the lean-rich exchanger, in the amine regenerator, in the reboiler, with potential carryover of oil into the close sulfur plant. So we can see circled on the sketch a particulate filter and liquid-liquid coalescer, very, very efficient oil removal, protecting the system from any sort of upset condition. On this application, we're recommending high flow filters as a first choice for particulate control and use of the FaceSep liquid-liquid coalescer due to ensure compatibility with the amine solution. These have shown excellent long service and excellent protection of the process loop overall, ensuring amine loop productivity, refinery productivity, and protection of the downstream sulfur plant. So that finishes the formal portion of today's presentation. We'd like to thank you so much for joining with us today to learn a little bit more about liquid-liquid coalescing and how these products apply to key refinery applications. If you have any follow-up questions, you'd like to learn anything more, please contact me, Robert James, at robert_h_james@paul.com. My office number, +1 905 363 4022, or cell +1 647 271 6607. I'll either do my best to respond to your requests directly or refer your request onto one of our subject matter experts, copying you on the request so you can keep track of the progress of the response. So I'd now like to open up the call for questions, and we'll be responding as those come in. Okay, we've got some questions coming in. You should be able to enter questions in the box on the left-hand side of the screen. So please check that out and send in. Starting off, we've had a question from Mukesh P. What are the points to be considered in scale-up of liquid-liquid separation? A very good question. One of the challenges with any liquid-liquid coalescer is to make sure that it is appropriately sized, and that an undersized coalescer will not achieve the efficiency that is anticipated. The higher flow conditions can cause re-entrainment of the droplets that are coalesced earlier on in the process. So we need to take in factors such as viscosity, density, interfacial tension on the fluids so that we can come up with an appropriate flux and an appropriate settling zone in the system. So we either base sizings on use of a sophisticated computer sizing program where we track past performance and use values that have been obtained to develop the proper sizing. And in newer applications, we also have availability of small-scale test rigs where we bring a small 6-inch long element on site and can flow and determine maximum flow capabilities on different applications based on specific application parameters. And then we have various scale-up factors that we use there to bring that to a full-size installation. We've been doing this for over 20 years now and find it a very, very successful process to evaluate any new application opportunity. We had another question. Interestingly, this one's from Mukesh B. How do we address dissolved salts which go with a condensate stream? It's an important consideration to get the sodium levels down in condensate. Cartridge-type liquid-liquid coalescers show very, very well on this type of application because their ability to go after the very, very fine droplets that are formed when you have the sodium present in the water. So often a lot of legacy equipment may have challenges getting out those fine droplets. A liquid-liquid coalescer will offer often significant improvements in not only the water removal, but also the sodium levels will be much lower on the downstream side. The other strategy that can be applied is to use water injection. This basically does a washing of the condensate and will give you further sodium reduction. And this can work up to fairly high levels of water injection. The coalescer itself can handle 3% water or higher levels. Not that you need to go anywhere near that high, but it just shows some of the capabilities on the product. Let me just jump to some of the other questions here. We've got a good extensive list. How does a Paul coalescer, such as an Aquacep XS, compare with a membrane separator? For example, a 0.5 hydrophobic membrane in analyzer sampling of final products. We get very, very high separation efficiency with the coalescer, so that we found excellent protection of analyzers with a coalescer. The 0.5 micron hydrophobic membrane could possibly give a higher degree of separation if you had dissolved contaminants that were an issue. But typically, if you're looking at a liquid-liquid consideration, the protection offered by particulate filtration and LL separation will give more than adequate protection to a typical analyzer. Question from Brian. Will Paul provide slides from this webinar? Most definitely. Should have mentioned that earlier on. For everyone who is registered on the seminar, we will be sending you a PDF version of the slide presentation. We would ask that you follow up from that. You'll also find additional materials on the Paul website if there's deeper interest to go into some of the theory on the coalescing process or all of the applications that were presented. You'll typically find a two-page flyer giving a little bit of additional detail on those. We've got a question here coming in. Yeah, here's a question. I'm having difficulty getting these to open up here. Please bear with me a moment. Is there an upper limit of free water that a liquid-liquid coalescer can efficiently remove? Good question. The standard sizing assumes that we would have a range of somewhere between 0 to 3% discontinuous phase coming into the coalescer. So the standard sizing program takes that into account. We do have applications where we can remove much higher water content. There was one that was installed in Western Canada a number of years back where we were running continuously on a 13% discontinuous phase, taking a water methanol mixture out of a propane stream. In that case, we needed to oversize the coalescer so that we had enough handling capacity with the additional number of elements. So pretty much as long as you understand what the conditions are on the front end, you can size it accordingly to handle the discontinuous phase loading. What is the ppm level in hazing of product? Very interesting question. It's interesting when you look at final product. The usual quality standard before something ships out is it clear and bright? So does it have that sparkle, almost like a nice glass of wine? What you'll find is a trained eye will start to determine a haze probably at about 20 parts per million by volume of free water. So that's part of the reason much of the specification on these products is to achieve a level of 15 parts per million by volume, so that on many applications where you have the need for clear and bright effluent quality, you will be able to achieve it. The untrained eye, you may be up in the 30 to 40 ppm if you're looking at a clear and bright specification. It's just looking for that tinge of change from true clarity to something with a bit of haze. But it's often the threshold where, hey, does it meet spec or does it not meet spec? And just scrolling through here. Is there a reliable method to calculate interfacial surface tension? Yes, there is a device for measuring interfacial tension. Basically what you would do is get a beaker of the two phases. So you may have an oil sitting on top of water. In the test equipment, what you do is it incorporates a stainless steel ring that you lower onto the interface between the two liquids. And then as you operate the device, it applies a tension to the ring and calibrates the force required to actually pull the stainless steel ring off of the interface. and the measure at which you actually pull the ring off of the interface is a measure of the interfacial tension. So this works very easily when you have heavier oils. It becomes more complex when you start to get into the lighter ends. There's more sophisticated processes there. If that's something of interest, I would ask that you get in touch. Question, do vertical liquid-liquid coalescers require level control on the aqueous phase being removed? Definitely, yes. As you're taking out discontinuous phase, there will be a requirement there to pull these out of the system. If you have very minimal levels of liquid, you may have a manual valve. You could just operate once a day, once a shift. If you're looking at more significant volumes, you will want to have automatic level control. That would probably include high and low level switching and high and low level alarm to give you enunciation if you ever have any issues there. We'll just handle one or two more questions and then wrap things up. If we're unable to get to your question during the presentation here, I'll seek to send you a written response shortly after the presentation. So we'll be able to respond to your area of interest. Question here regarding seawater and hydrocarbon from Youssef. Seawater can be effectively removed from any hydrocarbon with a liquid-liquid coalescer. The presence of the salt will typically give you a low interfacial tension, but certainly well within the range of what these products are able to achieve. Looking at the IFT scale, 0 IFT means that the two phases mix together. If you look at rum and coke, that is a 0 interfacial tension. We talked about how 20 dynes per centimeter is the area of difficulty for a standard glass fiber coalescer. We've used these products very successfully on interfacial tensions as low as 0.5 dynes per centimeter. Extremely challenging applications and ones that work well. So with that, we're a few minutes over. I'm going to look at closing things out. Once again, I would like to thank everyone for joining in. If I did not have a chance to get to your question here, I will be responding shortly afterwards. And please reach out to me if we can be of any further assistance. So thank you, and have a good balance to the day. Thanks again for your participation. Bye-bye now.